IPv4 addresses are made out of 4 octets, and they're also called dotted decimal notation. And we can break each of those numbers, each of the 4 octets, into the 8 bits they're comprised of, because data really is just zeros and ones. Anything else is just to make it easier for us and how we use it. For this SYSM certification, you don't need to dive too deeply into the binary math behind IP addresses, but you do need to have a basic understanding of how it works. It's much easier for us to say 172.16.254.1 than it would be to use the actual binary 10.101.0.001.000. That would just get confusing and annoying. You can see a breakdown here on the right of the IP address I've used and how each number would break into the binary 8-bit number. Each of the bits is assigned a number. The last bit is 1, the second 2, third 4, the fourth 8, and so on. So to get the number 1, we would get 7 zeros and then a 1. If we wanted to get the number 2, we would get 6 zeros, then a 1, and then a 0 again. The math calculation I have all the way at the bottom is for the 172. Take 172 minus 128. The first bit that indicates a 128, that gives us 44. Since 64 is bigger than 44, we don't do anything with the second bit. Then on the third bit, we minus 32. That leaves us with 12. 16 is bigger than 12, we don't do anything on the fourth bit. On the fifth bit, we minus with 8. 12 minus 8 leaves us with 4. And then the sixth bit, 4 minus 4, we have 0 left. So the 7th and 8th bit are zeros, which makes the binary value of 172 10101100. And that, I think, really is the extent you need to know for the exam. And just like we use dotted decimals instead of the 32-bit integers binary, we also use names for websites. It's much easier remembering google.com than it is to remember 66.102.12.231 or the equivalent IPv6 address. So you type in google.com in your browser. Your computer then goes out and asks, what's the actual address of this? And depending on if you use IPv6 or IPv4, you get either of those 2 replies back, or any of the other IP addresses Google uses. We do everything we can to make it as seamless as possible for the end user, and they don't see all the technical stuff behind the scenes. Another thing we did when we were starting to run out of IP addresses was we divided IP addresses into public addresses. Those are the ones that can be routed over the internet, and they're used to communicate between hosts over the internet. This could be internet routers, it could be websites, it could be anything like that. And then we made private addresses. Private addresses are addresses used for your internal network. Remember the example with the socket pairs earlier, where I had a 192.168 address? That's my private address. Your internet-facing router would have a public IP address. That's where all the traffic is sent. And then any device behind the router would have a private address. For private IP addresses, we have 3 ranges. The entire 10 network, all the way from 10.0.0.0 to 10.255.255.255, which gives an organization 16.7 million usable IP addresses, which can be very nice if you logically segment your network into different departments and different devices. The second range is 172.16.0.0 to 172.31.255.255. It gives you slightly over a million IP addresses. And then the final range, 192.168.0.0 to 192.168.255.255. That gives you about 65,000 IP addresses. Anything really outside that range is mostly public IP addresses. That's what we use to route over the internet. There are, however, a few exceptions. The entire address space for 127.0.0 is used for loopback IPs. They'll be on your PC only. You can see here I'm using a slash notation. This is /8. That means anything that starts with 127 is in that range. The link local range is most likely something you'll see if for some reason you don't have connection to your router or your switch. Then your IP address will show up with a 169.254 address. The last 2 octets can really be anything. If you see that IP address, you know there's some communication problem somewhere and you're not getting the IP address you're requesting. And then finally we have the broadcast address for IP. We talked about that already. 255, 255, 255, 255. Another band-aid solution we implemented when we were running out of IPv4 addresses was NAT and PAT. Static NAT translates 1-to-1. NAT means network address translation, and PAT means port address translation. In static NAT, we translate 1-to-1. So for every private IP we have that we want to be able to use the internet, we need a public IP, which really gives us nothing. We're still going to use the same amount of public IP addresses. PoolNAT was the next development, and it was slightly better. It's still a 1-to-1 translation. Obviously, we would still need as many public IP addresses as we have people that need to access the internet at the same time. If 25% of our staff need to access the internet, then we would need 25% of the number of private IP addresses we have in public IP addresses. We would still use a ton of IP addresses. So finally, they designed PAT. This is what you saw in my output from earlier. PAT uses both the IP and then a port number. It's also called one-to-many PAT. One-to-many NAT or NAT overload, since it translates one public IP into many private IP addresses. And that's what most of us use today. So remember, NAT is one-to-one. If it's static, you have to have one public IP address for each private IP address. If it's pool, it's a little more flexible. You have a pool of addresses that can be used, but once you run out, anyone else needing to access the internet cannot get on until someone stops using it. And then finally PAT, what we use today, one-to-many. Early on in the development of IPv4, it was very common to use classful IP networks, which means that every network has 16 million plus IP addresses, even if they only need 5 or 10. It was obviously a very inefficient use of the IP addresses, and people realized there would be a problem, so they designed classless IP networks. That's the slash notation you saw earlier in my IP address. It's either called a CIDR address or just slash notation, classless inter-domain routing. And we use CIDR notations to break our larger networks into smaller logical segments. First off, it saves a ton of addresses. Also, it allows us to make suitable networks for whatever we need. If I don't want payroll, human resources, and accounting to be on the same subnet and access the same files, I can logically segment each of them out. And depending on the CIDR notation or the slash notation, you easily know how many IP addresses are in that subnet. If you look at the IP address I had earlier, 172.16.254.1/24, I automatically know how many IP addresses that range has and what the broadcast address is. A /24 network is the most commonly used network. It has 256 addresses, where 255 of them can be used for hosts. To some people, the CIDR notation or the slash notation seems counterintuitive. The higher the number is, the less hosts we can have. If we're designing a network and we can tell we will never use 256 addresses, we might only need 10, then we can use a higher CIDR notation. We can build a smaller network just for that one segment. I probably be a little bit conservative when I assign IP addresses and assign bigger ranges even if we don't think we'll ever use it, because you just never know how networks grow. If we say we're going to use 10 workstations, for instance, I would maybe assign it as /27 or 26, which would have 32 or 64 addresses available and one less of that per actual host. So 31 hosts to 63 hosts we can have on that network. Then in 2 years, when that department all of a sudden grows tremendously, we can add another 20 hosts to it and never have a problem with reassigning IPs. In older networks, you couldn't use the first and the last address of the IP range, but now it's really just the broadcast address. In the /24, it's the 255 address we can't use. Everything else is fair game. Remember earlier in the OSI model or the TCP IP model, we talked about headers were added to each layer of the respectable models. This is how an IPv4 header looks. That's all the information that's in the header, not the actual data. It'll have a version number, in this case 4. Say how long the header is. If we're using quality of service, remember that's what we used to prioritize our important traffic and down prioritize the stuff that doesn't need real time. Then it'll have a bunch of identifications, flags, offsets, packet number if it's a TCP packet, and then the protocol. Is it TCP, UDP? What are we sending here? It'll have the source and destination IP. We can additionally add some options and some padding. Also, I'd be familiar with the term TTL, or time to live. Each packet has a certain amount of hops it can only go, and each hop is a router. What we use TTL for is to prevent routing loops. If for some reason we have 3 routers, they're all connected to each other, router A thinks it needs to send the packet to router B thinks it needs to send the packet to router C, and router C thinks it needs to send the packet to router A, the traffic is just going to go in a circle. It'll never go anywhere. So to prevent that, we'll have time to live. Every time a packet hits a router, it removes 1 from the time to live. If the time to live is 15 on router A, on router B will be 14, 13, and so on, the point where it hits time to live 0, the packet will be dropped. We are preventing a routing loop. We also use something called MTU, or Maximal Transmission Units, indicates how large a package can be for us to send it. Normally it's around 1500 bytes for an Ethernet package. If a package is bigger than that, a router might choose to break it down into smaller fragments so the packet doesn't exceed the size it should be. So let's look a little bit at IPv6. I guess you could say it's the new kid on the block. That's what we're moving towards, and that's a lot of what is happening on the back end. But really it isn't that new. It was designed and published somewhere in the mid-1990s. So even back then they knew we were going to run out of IP addresses. And then it just sat there for 15 years doing not much because, well, we still had enough addresses and it's difficult and it's expensive. And 50 other good reasons why we didn't implement. Then obviously at some point we had to because we ran out of IP addresses. And even adding some years to that was NAT and PAT. Each device didn't need an IP address anymore, so we could extend it for another 5 years. The reason why IPv6 addresses have so many more addresses is it's much longer addresses. And instead of using regular numbers, it uses hexadecimal. which means they can use 0 to 9, but they can also use A to F. An IPv6 address is divided just like an IPv4 address is, but with IPv6, it's 6 groups of 4 hexadecimals each. So an address could be FD01, FE91, AA32, and so on. You get the idea. But as I showed before, the address space is huge. We should hopefully never run out of IP addresses with IPv6. Another, for us, excellent built-in benefit as well on IPv6 is IPsec is built in. It's not just bolted on like it is with IPv4. IPv6 is slowly moving into organizations where they have dual-stack routers that can both understand IPv4 and IPv6. But really most of it still happens behind the scenes. The big use is the internet service providers, long-haul providers, the cell phone carriers, all the stuff behind the scenes that you'll never see. So for instance, the internet service provider I worked for in Denmark, which there was huge, but most places probably would be tiny. We had about 5,000 switches in our network, backbone core switches. It would be feasible for that company to switch all those to IPv6, and customers would never know. It's the same thing they did with the cell phones in the United States. Every smartphone in the United States, as far as I know, all running IPv6 because they can, and we have so many addresses, each address is not precious in the IPv6 range. For network admin or someone who's reading the IP addresses, IPv6 addresses are obviously more difficult to read, but there are a few things we can do to make it a little bit easier. Many addresses will have a lot of zeros in them. So once and only once, you can remove all the zeros you have in one row and add another colon. To the address I have over here on the right, where the last 4 octets are zeros, we can omit all those 4 octets and just add another colon. And if you're interested, you can see the hexadecimal numbers translated into binary below. IPv6 also does something that's a little bit smart when it comes to how it uses IP addresses and MAC addresses. Let's take an example where we use an EUI or MAC48 MAC address. Our MAC address is 00FA22528888A. Since this is an EUI48, we can't use it on IPv6. This is where IPv6 adds the FFFE into the middle of the address. So if you look over on the right, the top address is the address we have. The second address, right in the middle of the MAC address, you can see FFFE have been added in. It's now an EUI or MAC 64-bit address. It then changes the first octet to 20 instead. It's not really used for anything yet. It's made to allow the development of future technologies that can take advantage of interface identifiers with a universal scope. We then take that MAC address and we add our local prefix. In this case, let's just say it's 200100000000 B8. We then again remove the largest group of zeros we have and add another colon. Our IPv6 address using our MAC address is now 2001 B8 20FA 22FF FE528888A. And that would be the address we would use on the internet. And then for local addresses that are only used on our internal networks, we change the prefix for the first octet to be FE80 and then the same address all the way back. Each device will have a linked local address and a public address. We don't need NAT, we don't need PAT, we don't need any of that. We did to extend the range of IPv4 because each device can have its unique address that's used both on a local network and on the internet. The header of an IPv6 packet looks slightly different than IPv4. It still has the version number, in this case it would be IPv6, but some of the old labels have been renamed. Our traffic class of priority is really just our quality of service. The flow label is for quality of service management, then it has how long the payload, the actual data we're transporting is, the sequence of the next header, and then a hop limit. That's the one we call time to live on IPv4. That's the one that we decremented or lower for each router it hits. And then finally we have the source and the destination IP. These fields are obviously much bigger in IPv6, since we're no longer using 32-bit addresses, we're using 128-bit addresses. And the same applies with the MTU for IPv6 as it did for IPv4. If packets are too large, they get fragmented.